Last time we talked about the stability of the origin of a passive system when the forcing term, when the input is set to 0. Okay? And in particular, we obtained the following main results. The first one of the results was if you have a passive system with a post-definite storage function, and if you set the input of that system to 0, u equals 0, then the origin of that unforced system is stable. Okay? And we obtain stronger results under strict passivity and output strict passivity. Namely, we've discovered that for an unforced passive system that's strictly passive, the origin is asymptotically stable. Okay, and also for a system, for an unforced system that's output strictly passive, if the system has the zero state observability property, then again the origin turned out to be asymptotically stable. And with radially unbounded storage functions, the results can be extended to global asymptotic stability. Okay. In this lecture, we will be talking about passivity and stability properties of systems in feedback connection. So, by feedback connection, we mean the following. Okay. Feedback connection of two systems. We have the first subsystem, which we're calling H1, with input and output labeled as E1 and Y1. And we have the other subsystem, which we're calling H2, with input and output labeled as E2 and Y2. Okay, and now these systems are in feedback connection through the following topology. Here we have our first external input to the system, plus here we have minus, and here we have the second injection of the external input U2 plus and plus. Okay, so this overall connection now can be considered as a system with inputs U1 and U2, or you can just concatenate those two inputs and obtain the vector U with, and the output of the system is Y1 and Y2 considered together as a single vector. Okay. Now, suppose that each system H1 and H2 is represented by either by xi dot equals fi, xi, ei, and yi equals the alpha function of the ith subsystem. Okay, xi, ei. Okay, so if that's the case, then we call that system is dynamic. But we also allow static maps, okay, which appear in feedback connections a lot. Okay, so another possibility is that we have simply a static relation between the output and the input of the system. Okay. Hi of ei. And this system, since it doesn't have a state, it's called memoryless system. Okay, now we're going to make the assumption that the feedback connection is well defined, that is, for all initial conditions and for all inputs, U1 and U2, all the remaining signals uniquely exist, okay? E1, Y1, E2, and Y2. Feedback connection is assumed to be well defined. By which we mean for all possible external excitations, all inputs U1 and U2, the solution uniquely exists. Also, as usual, we're assuming that the function's right-hand side is 0 at 0, both for the right-hand side of the state equation and also the output equation. And hi 0, 0 equals 0. Okay. Or if the system is memoryless, then hi of 0 is 0, where I is the index, okay, of the system, either 1 or 2. Now, the first fundamental result about passivity is the following. It's very easy to keep in mind because it's a very elegant and short statement, and also it's very easy to prove, which we'll establish in a few lines. Theorem 6.1, feedback connection of two passive systems. Okay, so the resultant closed loop, if H1 and H2 are individually passive, the resultant closed loop must also be passive. Okay, a very simple, elegant result. The feedback connection of two passive systems itself is passive. Okay, now let's prove this theorem. And then we will move on to more elaborate results. Okay, so what we have to do is, well, we're going to use the definition of passivity, okay, and then we're just going to look at the connection and use the relations between the signals that appear in our connections, like E1 is E1 minus Y2, or E2 equals Y1 plus U2. Okay, here is the demonstration. Let V1 and V2 be the storage functions, respectively, of the subsystems H1 and H2. If one of those systems is memoryless, then you can simply take the storage function to be 0, because for the passivity definition of a memoryless system, we don't, the definition doesn't need a storage function. Okay, so let V1 and V2 be the storage functions, respectively, for subsystems H1 and H2. Okay. If one of the systems, or even both, is memoryless, okay, if the ith system is memoryless, simply take the storage function to be 0. Take the corresponding storage function to be 0. And now we can proceed as follows. We're going to obtain the passivity of the interconnection, and not surprisingly, the storage function that we will use to obtain the passivity of the closed-loop system will be simply the sum of individual storage functions. Okay, v1 plus v2. Okay. So what we have is e1 transpose yi. So the input and the out, the inner product of input and output of the ith system is greater than or equal to time derivative of a positive semi-definite function, which we call the storage function. Okay, vi dot. So that's the definition of passivity. If the system is memoryless, the definition is simply is this inner product is greater than or equal to 0 for all inputs vi. Okay, so that's true for both I equals 1 and I equals 2 because we're assuming that both subsystems are passive. Okay, two passive systems. Now, from this, it's very easy to obtain the passivity of the overall connection, the closed-loop system, if you choose the storage function of the closed-loop system to be sum of the individual storage functions, v1 and v2. So define the overall storage function. V of x as v1 of x1, where x1 is the state variable of the first subsystem, plus v2 of x2, where x2 is a state variable of the second subsystem. Suppose that second subsystem is memoryless, it's just a nonlinear game, let's say. In that case, v of x simply is v1 of x1. Okay. And where x is our state variable of the new closed-loop system, x1 and x2 considered together as a single state vector. Then, what we require is that our storage function, okay, by definition of passivity, our storage function v dot must be less than or equal to the inner product of input and output of the closed-loop system. And input and output of the closed-loop system is the following. Input is u1 and u2 considered as a single vector, okay? And the output of the closed-loop system simply is this y1 and y2, okay? So what we need to show is the inner product of these two signals always upper bounds the time derivative of the storage function that we constructed using the individual storage functions of these subsystems. Okay. Then we have v dot equals v1 dot plus v2 dot. Okay. Because v is v1 plus v2. And that's less than or equal to what? v1 dot is less than or equal to e1 transpose y1. Likewise, v2 dot is less than or equal to the inner product of input and output of the second subsystem. Okay. And then let's replace e's, e1 and e2, by expressions in terms of input and output, u and y. So what's e1? e1 is u1 minus. Okay, so this is e1. e1 is u1 minus y2 transpose y1 plus what's e2? e2 is this signal and it's simply y1 plus u2. u2 plus y1 transpose y2. Okay. And then what we have is this minus y2 transpose y1 term will cancel y1 transpose y2. Okay, and we'll be left with u1 transpose y1 plus u2 transpose y2. Okay, and since u and y are defined as that or constructed as that, this is the input of the to the overall closed system, and this is the output from the overall closed system. This sum is exactly the inner product of the new input and the new output. So therefore that equals U transpose Y. And what we have obtained is, we have a storage function and its time derivative is less than or equal to the input product of the input and the output of the closed system. Therefore, by definition, the closed system is passive. Now, let's also talk about the L stability of this feedback connection. And throughout this lecture, we'll be using this fact a lot. Okay, this thing, okay, equals that thing. And this equality will be very useful in our further demonstrations for the results to come. Here's another nice, neat result. It's about L2 stability of passive systems, or interconnection of passive systems. The feedback connection, okay, and by feedback connection we mean what we defined in the beginning of the lecture, okay, that block diagram, the feedback connection of two output strictly passive systems with EI transpose YI greater than or equal to VI storage function dot plus some constant, then YI transpose YI. Okay, so that system is output passive with a linear rho function. Remember the general definition. In the general definition, we use a function of the output, which we call rho, and here we have Y transpose rho phi. In this case, rho phi is simply delta I times, or delta I times Yi, okay, for each subsystem. Okay, so if the feedback connection of two output passive systems, where the storage function satisfies the following property, is where delta I is positive, delta I positive is finite gain L2 stable with L2 gain no larger than 1 over the minimum of two deltas, delta 1 and delta 2. L2 gain no larger than 1 over min delta 1 and delta 2. Okay. And now here goes the proof. As before, we're going to be using, in fact, we will always be using the sum of individual storage functions to construct the storage function for the overall closed loop system, for the feedback connection. So let V be V1 plus V2, sum of individual storage functions, and let delta indicate the minimum of both delta i's, okay, delta 1 and delta 2. Delta 1, delta 2. Delta 1 is positive, delta 2 is positive, therefore the minimum is also a positive constant, delta. Okay. Then U transpose Y equals, okay, U transpose Y, we mean this and this, equals, because of our feedback connection, one with the minus, one with the plus sign, that equals E1 transpose Y1 plus E2 transpose Y2. Okay? So Y1 plus E2 transpose Y2. And that's greater than or equal to. Now E1 transpose Y1 greater than E1 dot plus delta 1 Y1 transpose Y1. And likewise, E2 transpose Y2 greater than or equal to E2 dot plus delta 2 Y2 norm square. Hence we can write V1 dot plus V2 dot plus delta 1 norm square of Y1 plus delta 2 norm square of Y2. Okay. And that clearly is lower bounded by V dot. So V1 dot plus V2 dot by definition is V dot. And this thing can be lower bounded by delta Y transpose Y. Okay. Then the result follows from an earlier lemma that we considered in one of our previous lectures. Follows from lemma 6.5 from the text. Okay, now let's apply this result, or a simple variation of this result, to an example. Consider the feedback connection of the following subsystems. Okay, H1 and H2, where H1 is given as the following dynamic system, second order, with single input, single output. X1 dot equals X2, X2 dot equals minus A, X1 cube minus B, X2 plus E1, the input to the first subsystem. Okay. And Y1, the output of the first subsystem is the second state variable. As for the second subsystem, it's memoryless. It's just a simple input-output map, and that map is given to be linear. Okay, Y2 equals K times E2, and K is, for instance, an LTI resistor, and K is positive, with A, B, K, the system parameters of H1 and H2, all being positive constants. Now, we will show that the feedback connection of these two systems is L2 stable, and we're going to figure out the L2 gain for that connection. Let's do that. Let V1 of X, the storage function, for the first subsystem is X1 to 4 plus 1/2 X2 squared. Okay, let's look at V1 dot, and by looking at V1 dot, perhaps we will obtain some passivity property regarding the first subsystem H1. So V1 dot equals what? A X1 cube X1 dot plus X2 dot. X1 that is here, X2 that is here, we can write that equals A X1 cube, X1 dot is X2 plus X2 times X2 dot is here, minus a x1 cube minus b x2 plus e1. Okay. Now here we have a x1 cube x2. Here we have minus a x1 cube x2. Therefore, this and this, they cancel out. And what we have is v1 dot equals minus b x2 squared plus x2 e1. Now x2 is the second state variable, which is given to be the output of the first subsystem. Therefore, what we have here is minus b y1 squared plus the inner product. Well, in this case, because it seems like scalar, just the product of the output and input of the first subsystem. Okay, so clearly, since it's supposed to semi-definite function, in fact it's a positive-definite function, it's a valid storage function candidate, and storage function candidate's time derivative equals a negative definite function of the output plus the inner product of input and output of the first subsystem. Therefore, the system is output strictly passive. Okay. So let's call this equation 1. Also, for the second subsystem, we have E2, Y2. In this case, the second subsystem is memoryless, that we don't have to check for a storage function. Okay. All we have to do is we have to look at the product of, or the inner product of the output and input. E2, Y2 equals 1 over k Y2 squared. That's equation 2. That tells us that the second subsystem is passive. 2. Now, by combining 1 and 2, we can obtain the passivity of, output strict passivity of the connection. So let's do that. Then, by 1 and 2, we have the following. V1 dot equals minus b y1 squared minus 1 over k y2 squared plus e1 y1 plus e2 y2. Okay, so what we did basically is we just rewrote equation 2 as e2 y2 minus 1 over k y2 squared equals 0. Okay, and then we sum equation 1 and equation 2. Since this is 0, we can add it to the right hand side of equation 1 without disturbing the equality. And when you do that, this is what you obtain. This can be written as, okay, or bound by minus min bn 1 over k times y1 squared plus y2 squared. Okay, so this term here can be upper bounded by this minus the minimum of bn 1 over k times the norm square of the overall output. Also, from the previous arguments, we know that for our feedback connection, this sum equals u1 y1 plus u2 y2, where u1 and u2 are the external inputs to our feedback connection. We have that for u1 y1 plus u2 y2. Okay. Hence, we can write v1 dot equals, v1 dot plus min b 1 over k y transpose y, where y is y1, y2, and u is u1, u2. Okay, that's less than or equal to inner product of U transpose, the inner product of U and Y. Therefore, by lemma 6.5, we have that this system is L2 gain finite, gain L2 stable, and the gain is not larger than 1 over this. Okay. L2 gain no larger than 1 over min B and 1 over K. Okay, so that's the those two results that we've seen. Presents how the passivity properties of the individual subsystems is inherited by the newly formed, newly constructed overall closed-loop system. Okay, for the feedback connection that we consider. Now, what we're going to consider is what happens for the feedback connection when you set the inputs to 0. Okay, so what we're going to do is we're going to take two passive systems, obtain the feedback connection, okay, obtain the closed-loop system, set the input, external inputs to that closed-loop system to 0, and we're going to analyze the stability properties of the origin of that unforced closed-loop system through passivity arguments. And our first result is the following. It's theorem 6.4 from the text. So again, what we consider is, we consider the feedback connection that we have drawn on the board a couple of minutes ago. So for that feedback connection, the subsystems H1 and H2 satisfy the following properties. H1 is strictly passive. And H2 is a memoryless system. Which is passive. And then for this interconnection, we're going to set the inputs, the external inputs to 0. And it turns out that the origin of the closed-loop system in that case is asymptotically stable. Okay. Furthermore, if the storage function for the first subsystem, not that we don't have a storage function for the second subsystem because it's memoryless, storage function of the first subsystem, which can be used as the Lyapunov function for the overall closed-loop system. If it's radially unbounded, then the result is true globally. Okay, so we have global stability for the origin. Okay, under that assumption, then the origin of the unforced closed-loop system, in other words, closed-loop system when U equals 0 and U is our input vector to the closed-loop system, is asymptotically stable. And furthermore, if the storage function is radially unbounded, H1 is radially unbounded, then the origin of the unforced system is globally asymptotically stable. The origin is globally asymptotically stable. Okay? Now we're going to establish a demonstration for this for this statement. Okay, so here goes the proof. Not surprisingly, we're going to be working with the source function of the first subsystem as the Lyapunov function candidate for the overall closed-up system. So let V1 be the storage function. Function for the first subsystem. Remember, that second subsystem doesn't even have a storage function because it's memoryless. X1 equals F1 of X1 E1, Y1 is H1 of X1 E1. Then, by definition of strict passivity, there must exist a positive definite function of state X1 such that V1 dot is less than or equal to the inner product of input and output E1 transpose Y1 minus that positive definite function of state X1 for some positive definite psi 1. Excuse me. Then we will use this fact E1 transpose. Okay, so we have been using it all the time. E1 Y1 plus E2 Y2, or E1 transpose Y1 plus E2 transpose Y2 in our feedback connection equals the product of input and output of the closed system. Okay. Using that plus the fact that the product of E2 and Y2 is never negative because the second subsystem is passive, we will obtain what we want. So note that note that E1 transpose Y1 plus E2 transpose Y2 equals U transpose Y. Okay. So that's the peculiarity coming from our feedback connection. Okay, and it's true regardless of what these subsystems are. And in this case, we're considering that the external inputs to the system is 0, therefore U is 0, meaning regardless of the outputs that may be generated, this inner product is 0. Okay. Therefore, what we have is this thing, E1 transpose Y1 must equal minus E2 transpose Y2, because this sum equals 0. Hence, and we can write E1 dot less than or equal to. Now we can replace this E1 transpose Y1 by minus E2 transpose Y2. Minus E2 transpose Y2 minus psi 1 of X1. Okay. And by passivity, this inner product is never negative, therefore this is never positive. Hence we can remove this term without disturbing the direction of the inequality sign here. Okay. Also, H2 passive implies that the inner product is never negative, E2 transpose Y2. And that yields V1 dot less than or equal to minus psi 1 X1. Okay, let's call this inequality 1. Okay. And from an earlier result, we know that if a function's time derivative can be upper bounded by a negative definite function of the state, then it must be that that function, V1, must be positive definite. So we have proven that in our previous lecture from the proof of one of our previous results, which was lemma 6.7. If you recall, that strict passivity automatically implies that the storage function is positive definite. Okay. Then what we have is follows. What we have is we have a positive definite function of state x1, and that positive definite function satisfies this strict decrease, okay, through its time derivative. Therefore, by Lyapunov's theorem, the origin has to be asymptotically stable. Furthermore, if the storage function is radially unbounded, then we have, again by Lyapunov's theorem, global asymptotic stability. Okay, so that's the end of our demonstration.